Hello everyone. So in this video we are going to do a very brief and quick recap of various topics in magnetostatics. Okay. So in the last video we have done a recap of various topics in electrostatics. So in this video we are going to discuss magnetostatics. Okay. So again our starting point is basically these set of fundamental equations and so this so we have so as I said, as we had discussed before, there are these Maxwell's equations where which are essentially can be thought of as the equations which tells us what the electric and magnetic fields will be given some sources, and these sources can be in the form of charge density or in the form of current density. And so now let's say that we are given some electric and magnetic fields. Then if you ask that how is that going to influence the charges, then that is given by the Lorentz force equation, where you have to the charges themselves experiences a force due to some existing electric and magnetic fields, and that is given in this formula here. Okay, so now in the previous video we have learned how to write down the charges in terms of, let's say, even if there is a point charge, we can use the delta function and write it down in terms of charge density, right? And so similarly we can write down use the delta function and write down a current density for a single moving charge as well. Okay, that we have seen in the previous video. So using that, we can now say that we can write down a corresponding local force experienced by some charge distribution or current distribution, and what we can say is as follows. We can convert this force into a force density, which is like a force field which exists, let's say, in a region, and this density is nothing but the charge density times the electric field. So all these things are functions of space and time in general, and so here this is the charge density times the velocity of every point where the charge density is non-zero. So that is the velocity of every point where the charge density is non-zero. So it's the velocity of every component of the charge density, if you like. And that this is basically this V cross V is the magnetic force on such moving charge densities. Okay, so this we can compactly write down as charge density times electric field and current density cross magnetic field, and this is a local expression for the force, if you like. So this is like a force field, and we can take this force and integrate it over a given volume, and if we integrate it over a given volume, then we will recover. If we integrate it over a given volume, then we can compute the force on an arbitrary charge distribution or a current distribution. Okay, so in fact, if the current density and the charge density are given by delta function, if we do that integration over some volume which contains this charge density, a single charge and a let's say a single moving charge, then basically from there we can immediately get back this, because the delta function clicks only at the location of the charge, and that will give us this original Lorentz force equation. Okay, so this is, if you like, a continuum version of the Lorentz force equation, and that is why I am calling this a force density. If you integrate the force density over a volume, you get the total force acting on a, let's say, given charge configuration or current configuration. So this is what will be very useful. This idea is very useful. So as we have seen, so now we can write down all the equations in a somewhat local form, that where we consider everything is like a field or a function of space and time, and here the electric and the magnetic field is given in terms of charge density and current density. Even when we have a single point charge or single particle which is charged, even then we can just use the delta function and write it as a continuum charge density. Okay, so that is the idea. Anyway, so that is the starting point. But as we have done in case of electrostatics, in magnetostatics, we are also going to think of this magnetostatic problem as a particular ansatz. So we'll call this the magnetostatic ansatz in contrast to the electrostatic ansatz. And so this is again going to be a simplifying assumption on the fields and the sources here for this equation, which will allow us to solve the equations very easily. And these are essentially a second set of simple solutions to the Maxwell's equations. And so what is this ansatz? Let's see. So this ansatz is basically, it says that, we will not consider any electric field or charge density. Okay, so E is 0 and the charge density is 0. And what we're going to consider are non-zero currents, which are called steady currents, that is independent of time. So these are steady currents we are going to consider. These are essentially sources which are present in this Ampere's law or this Karlov B equation. Okay, these are sources which is present here. So this is going to be non-zero and it's going to be independent of time. Therefore, they are steady currents, and the magnetic field will be non-zero, but it will again be independent of time. Okay, so it will be independent of time, and so this will be our ansatz for magnetostatics. Okay, so as you can see that with this ansatz, that if we say that nothing depends on time, neither charge density nor current density nor the electric and the magnetic field, then these two equations decouple, because if there is no time dependence, this term will go away and this term will go away, and then these two equations are the same set of equations in electrostatics, and these two equations are the equations that will survive in magnetostatics. So you can think of a system where you are doing both the electrostatic and the magnetostatic problem together, but you can solve the equations separately. Electrostatics, we have already seen how to deal with those equations. Now it is time for us to see what the solutions of these magnetostatic equations are. These are these other two equations. Okay, so if we assume time independence, then these equations decouple, and there is no coupling between the electric and the magnetic field as such, and therefore we will essentially move to we will discuss both electrostatics and magnetostatics separately. Okay, so I must say here, one thing, when we discussed electrostatics, we definitely made such an ansatz where magnetic fields were at 0, and these two so basically these two equations where magnetic fields and currents were at 0, these two equations were automatically satisfied then, and then these two, the Gauss law and the Faraday's law, they were the two equations that we solved for electrostatics. Now I should say here that let's say you are given an electrostatic problem. Of course, what you can do is you can start moving with a constant velocity, let's say, and then the electrostatic problem is not an electrostatic problem anymore because the charges are moving. Okay, so in that case, what we are doing what we have done for electrostatics, we are saying that there exists a frame where this ansatz is valid, that where things are stationary and nothing depends on time, and basically we are going to work in that frame and write the solutions in those frame. Of course, things become very interesting when we start moving with constant velocity, and this will bring us to the context of relativity, and this will see what happens there. Again, in the later part of the course, we'll see what will happen there. All right, so with this is our magnetostatic ansatz. Let's just quickly see what our equations reduced to under this ansatz. So the Maxwell's equations reduced to these two equations. One of them says that the divergence of the magnetic field is 0, and the other one says that the curl of the magnetic field is basically the current density. Okay, again, these are two local equations which is valid point by point everywhere. Okay, so before we proceed, we can just see that the following fact. So we have seen that in the full set of Maxwell's equation, there is a constraint on the sources, and that constraint is basically interpreted as the conservation of charge. And that statement is the time derivative of the charge density plus the divergence of the current density. This is equal to 0. But now, because the charge density itself is 0 and nothing is dependent on time, therefore you can expect that in the magnetostatic case, this just reduces to the divergence of the current density equal to 0. Okay, so in the electrostatic case, this equation is trivially satisfied, because in electrostatics, J equal to 0 and rho equal to rho independent of time, right? So J equal to 0 and rho of x and t is equal to rho of x. Okay, so in this case, basically del T of rho plus divergence of J, this is trivially satisfied for electrostatics, because time derivative will kill this and J is 0. Okay, but for magnetostatics, current density is not 0. It can be a non-trivial function of space-time, and but it should be true that the current conservation is valid, and that would simply imply that the divergence of J equal to 0. Okay, so this can also be seen as a consequence of this equation. Okay, this equation, as you will see that, this is related to the Ampere's law. Very soon we'll see that. Now, this equation, if we take simply if we take a divergence on this equation, then we will have a divergence of curl of B that is going to be 0. Again, you can use your epsilon notation to write down the curl to see that this immediately vanishes. But if we take the divergence, then therefore this would imply that the divergence of J, this is equal to 0. And so that is like a consistency condition on this steady currents that we have. Its divergence of the steady current must also be equal to 0. So we have the magnetic field whose divergence is 0, we have the current density whose divergence is 0, and the curl of the magnetic field is equal to the current density. The current density in this problem is to be thought of as a given quantity, that given some current density, you want to find out what is the corresponding magnetic field produced by that current density, and this set of equation is going to tell you what the magnetic field is. Okay, so now with this, let us try to look at this first equation a bit closely. And maybe you have most of you have already seen the Ampere's law in this form, and so let me just very quickly give you a little bit of a reminder of Ampere's law. So what is done here, that let's say we have these local equations that is valid point by point, and we take a surface like this which has a boundary. This del S represents the boundary of the surface S. This standard notation. Okay, so S is the surface, del S is the boundary, but because S is a surface, therefore this boundary is a closed curve C. Okay, so that is the notation. So now if we take this equation and integrate it over a surface like this, over the surface S like this, then this will give on the right hand side, this will be the total current that is flowing through the surface. This is by definition of the current density, that if you take the current density and integrate it on a surface, okay, then that gives the current flowing through the surface. So this is like directly the total current flowing through the surface S, right? But here on the left hand side, it becomes very interesting, because this curl of B, the surface integral of the curl of B, this can be written down using Stokes' theorem as the line integral of the magnetic field along the closed curve C. So if we take this closed curve, we can perform the line integral of the magnetic field, and that should give me the mu naught times the total current that is passing through this surface that this line, this closed loop encloses. Okay, so this is the statement of Ampere's law, and you may have learnt it that way, that given any loop, if we consider the line integral of the magnetic field around that loop, then that line integral would be given by the total current which is passing through this loop times mu naught. Okay, so that is this thing of this is the statement of Ampere's law. Now, once we say it this way, then there is a question. Then there is an immediate question. The question is that, you see here what I'm saying, there is a loop, and I'm doing the integration of the magnetic field around this loop. But when I'm saying that there's a current which is passing through, I'm considering the surface that this loop encloses. Okay. Now, a loop can enclose, many kinds of surfaces, as is shown in this figure. Let's say, there's this loop here, which I'm denoting by C. Now, you can take this loop and close it, just by a plane like this. Okay, that is your surface S1. Okay, so S1's boundary is also this loop, this thing. But you can also make it like a pot, like like the surface of a pot, like this, okay, which also like has this surface here, and this is the surface S2. But this surface S2 also has a boundary, which is basically this loop, the same loop C. So both these two surfaces have the same boundary, which is this loop C. Similarly, you can draw many other surfaces which satisfies this condition, that its boundary is basically this closed loop C. Now the question is, then in Ampere's law, then what I'm saying here, on the left hand side there is this loop, right? That is unambiguous, that there is this loop C. But on the right hand side, I have to consider a surface that whose boundary is this loop, and then I have to find the current through it. But the surface, such a surface whose boundary is this loop C, that surface is not unique. In fact, there are infinite number of such surfaces. So, in order to calculate the current, which surface should we consider? That's a question, right? Which surface should we consider? And the answer to that question is, it does not matter. You can consider any of the surfaces and it will give you the same answer. That's the point. As long as you are in magnetostatics, you can consider any surface you want, you will get back the same answer. Alright, so here is how to see this very quickly. The reason for this is the fact that the divergence of the current is zero. Okay, and so how to see that? So let's try to consider this figure again here. Okay, so here we have, let's say you consider two surfaces, S1 and S2, that I described to you before. Okay, and if you consider the current which is passing through S1 and S2, and if you add them up, then basically you will get the total current which is passing through the closed surface S1 and S2. You see, this S1 and this S2, they form a closed surface, and that closed surface encloses some volume, right? So basically S1 plus S2, they will form a closed surface. As long if they are ending on the same curve C, they will form a closed surface. And this closed surface S1 plus S2 will enclose a volume V, which is inside, this surface. But this has to be a closed surface because both S1 and S2 ends on the same curve C, right? So this has to be a closed surface. And if we take this closed surface and this volume V, which it encloses, then we have this current which is flowing through this closed surface S1 plus S2. Then by using divergence theorem, we can write this term as the divergence of J integrated over the volume V, whose boundary is this closed surface S1 plus S2. Okay, so now we know that the divergence of G vanishes locally everywhere within this volume, so this integral must vanish. And that means that the integral of the current through S1 should be the integral of the current through S2, apart from a sign. This sign has got to do with the fact that when you consider them together, then this has to be the outward pointing normal, but when you are considering the currents, they have to be directed in the same way. Okay, so that's the reason why the sign comes, but the magnitude of the current in both the cases through both the surfaces, that's the same. And if you consider the surfaces pointing in the same direction, then basically the direction of the current is also the same, right? In this case, what happens while applying divergence theorem, we need to consider the outward pointing normal, and for that outward pointing normal for S1 is in a direction, and for S2 is in a opposite or different direction. Okay, so that is the reason for this sign, but this simply demonstrates that the current which is passing through S1 is the same as the current which passes through S2, provided the divergence of the current is zero. Okay, so provided that we are in magnetostatics and the divergence of the current is zero, then this fact is true, and we can take any surface which this loop encloses and then find the current through it, and we will get the line integral of the magnetic field. Okay, and that's Ampere's law for you. Very good. So now we can immediately see this in an application here, in an example. For instance, let's say you have this infinite conductor. Okay, so there's an infinite wire which is conducting some current I. Okay, so now if this is conducting some current I, then by rotational symmetry, you would know that the magnetic field that this creates should not depend on this angle phi. Okay, it should not depend on this angle phi, and it should only depend on the distance of the point from this wire. Okay, so therefore for this problem, the cylindrical polar coordinates is the most suited coordinates for this problem. Let us consider this problem in cylindrical polar coordinates, and let's say this phi and this rho is the radial direction and the angular direction in the xy plane, and let's consider the direction of the wire to be the z direction. Okay, so in this setup, if we use the symmetry of this problem, and if we consider a line, a loop, which is basically a circle on the xy plane, which is centered around the wire. So basically the wire is the z-axis and this is the xy plane. Okay, so this is xy and this is z, and so we are considering one loop on the xy plane, which is this loop is perpendicular to the z direction. I mean this loop is like in the xy plane essentially, and so basic, but the center of this center of this loop coincides with the point through which the wire is passing. Okay, so that is my line. And now if we take this line and if we make this ansatz for the magnetic field, that the magnetic field is basically it's a function of r, and excuse me, it is a function of r. The magnetic field is a function of r, and again, by the symmetry of this problem, the magnetic field is basically directed along the phi direction. So this is the ansatz for the magnetic field B of r phi hat, which also happens to be, this phi hat also happens to be the direction of a little line element on this circle. The direction of the little line element is also along the phi hat direction. So now putting everything together, you see, with this assumption for the magnetic field, we can write down the line integral of the magnetic field for this current carrying wire. It is the magnetic field created by the current in the wire. So if we take that and if we compute this line integral, then of course phi dot phi, that's going to be 1. And then we are left with this line integral, simple line integral, not a vector line integral. And that this is essentially the circumference of the circle, which is 2 pi r. And we are left with B of r here, because we can take this outside, because r doesn't depend on phi, it just depends on the radius of this circle. And then that is equal to mu naught times the current passing through a surface which is enclosed by this circle, and that current is always going to be I, which is the current carried by the current carrying conductor. So this is just a fact which is valid for a circle of any radius. Because it is valid for a circle of any radius, therefore B of r for any value of r has this form that it goes as 1 over r, and the B vector is directed along the phi direction and it goes as 1 over r. So this is very much like using Gauss law or drawing Gaussian surfaces, exploiting the symmetry of the problem. And we can draw line, now consider line integrals of the magnetic field, exploit the symmetry of the problem, and thereby find out what is the magnetic field in various situations. Okay. But we have to be very careful that if the current distribution is not symmetric, then this kind of logic immediately don't apply. So basically this ansatz for the magnetic field is very crucial to solve this problem. And this ansatz would generally not be true if you have some arbitrary current sources. It's only because we have this one single line, current carrying wire, and that is why this kind of ansatz is valid, because of the symmetry of the problem. So one has to keep in mind, if one uses techniques like this, one has to keep in mind that whether the symmetry is there in the problem or not. If the symmetry is not there, this kind of tricks cannot be used, and then we have to resort to some direct solutions, which we'll see later on in this video. All right, now, so without further ado, let me now immediately move on to this discussion of the vector potential in magnetostatics. So this is the analog of the story. So if you remember from your electrostatic story, there was this scalar potential that we could define And we could write down the electric field in terms of the scalar potential. Basically, the electric field is minus gradient of the scalar potential. And the reason why we were able to write the electric field in terms of the potential in electrostatics is that the curl of the electric field was equal to 0. But here, we have the magnetic field, which is non-zero. Here we are not worried about the electric field, but we are worried about the magnetic field in magnetostatics. And we observe that the divergence of the magnetic field is equal to 0. Now, whenever there is a divergence of a field is equal to 0, then it is possible to write the field as the curl of any other vector field A. Okay. So this is always possible. As you can see, if we take the divergence on this, then it will be the divergence of the curl, and that has to vanish, right? So any vector field whose divergence vanishes can be written down as the curl of another vector field. Okay, and this, in this case, if we write down the magnetic field as the curl of a vector field, then this vector field is known as the vector potential. Okay, this vector field is known as a vector potential, and as soon as we write the magnetic field down in terms of the vector potential, one of these equations is immediately solved. Okay, one of these equations is immediately solved. So to conclude, let's see what happens. So initially we started off with this full set of equations, which are these set of Maxwell's equations. On top of the Maxwell's equations, as soon as we did the magnetostatic ansatz, E equal to 0, rho equal to 0, that implied that this equation and the Faraday's law, these are satisfied immediately. If E equal to 0, rho equal to 0, well, the Faraday's law is satisfied because B is independent of time as well. So Faraday's law is satisfied. These two equations are satisfied. While these two equations, one of them remains as it is, the divergence of B equal to 0, and the other one, this term drops out from the other one, and we are left with the curl of B equal to mu naught J. So that was the Ampere's law that we discussed. And so for magnetostatics, there are two set of equations to solve: the divergence of B equal to 0 and the curl of B is equal to mu naught times the current density. And these two equations are immediately, among these two equations, this one, divergence of B equal to 0, is immediately solved if I write down B in terms of a vector potential, writing it as a curl of some vector potential. Okay, so this equation is solved and we can forget about it, and we can now try to see what the Ampere's law implies for the vector field. Okay, for this vector potential. So if we take this and plug it into Ampere's law, we get this expression for the vector field. Right, so basically here the curl of curl, that thing I have used, there's a vector identity, right, where we can write the curl of curl as the Laplacian acting on the vector field, and this one is the gradient of the divergence of A, that is equal to mu naught times current density. Okay, this is what we get here. If we again, if you are, I think I gave you this identity as an exercise in your problem set 1. So you can just write these curls out in terms of the epsilons, and once you write that out in terms of the epsilons, you will see that this formula just follows from here. Okay, and then there would be two epsilons because there are two curls, and there will be one index that is contracted between the epsilons, and that is going to, so then you can write the two epsilons in terms of the deltas. So basically that will give you two terms, and these will be the two terms, right? So very good. So and another thing that immediately followed from this equation was that the fact that we discussed that the steady currents that we consider, time independent steady currents, they also have to be divergence free. They have to be, the divergence must vanish. Okay, it's a consistency condition because of Ampere's law. Okay, so very good. So now therefore we are reduced to solving this one equation for the vector field. The vector field has three components, and we have three equations here. And so basically, this equation has a source, which is this current density. The only thing is that this current density, the divergence has to be equal to 0 in magnetostatics. And so now we just have to solve this equation. And if we can solve this equation for an arbitrary current density, then we would have solved the magnetostatic problem, just like we solved the electrostatic problem. Okay, so we solved the electrostatic problem in terms of the scalar potential, and we solved this Poisson equation. And now we have to solve this equation, but this equation seems to be more complicated than just Poisson equation, because there is this term, of course. Okay, there's a Poisson equation like structure. There's this Laplacian acting on the vector field, but there's also this term which is proportional to the divergence of the vector potential. Okay, so let us pause here and let us try to appreciate one very important fact which is going to become very, very important later on. We have to appreciate this fact, and this fact is the following fact, that if you write this magnetic field in terms of the vector potential, then the following happens. So you see, there's a very interesting thing that goes on here. Okay, so this is something very important. So please try to pay a little bit of attention, and this may be slightly new to some of you at least. Okay, so let's say you have a gauge potential here. Okay, sorry. Let's say you have a vector potential here. Okay, which is this, which is given by, which I am denoting by A1, whose curl is giving this magnetic field V1. Okay, so now let me assume that there is another vector potential which is related to the previous vector potential. Okay, this A2 is another vector potential which is related to the previous vector potential through this is the previous vector potential plus the gradient of a scalar field, which is chi. Okay, this chi is a scalar field, and so basically the A2 is related to A1 by the gradient of this scalar field chi. Right, now if such a A2 exists, okay, that always exists, because you can always take A1 and add to it the gradient of any other scalar field chi. You can always construct another A2 which has this form. Now once you have constructed this A2, then let us see what is the magnetic field corresponding to this A2. So the magnetic field will essentially be the curl of this A2. Now if I write it down in terms of A1, so I will write it down, it's the curl of A1 plus this gradient of chi, where this is the scalar field. Chi is the scalar field. Okay, so if that is the case, then you see there are two terms. One is the curl of A1 and the other is the curl of the gradient on chi, and the curl on a gradient that vanishes, as you all know very well. So basically this is again the curl of A1, which is equal to B1. So basically under this shift of the vector potential with the gradient of a scalar field, it can be any scalar field, we can shift it with the gradient of a scalar field. Okay, if we shift it with this any gradient of any scalar field, then under this shift the magnetic field which this vector potential represents remains unchanged. That is what we saw. Now this therefore, this chi, the scalar field therefore represents a redundancy in the description of the magnetic field in terms of the vector potential. Because whatever vector potential you give me as a solution to a problem, I can add to it another gradient of some chi, any choice, I can choose chi to be anything and add to it. That will be a different vector potential completely. But both these two vector potentials represent the same physical scenario, because magnetic field is the physical thing that we go ahead and measure. So because these two vector potentials represents the same physical scenario, therefore these two vector potentials are redundant descriptions, or the second one is a redundant description of the same physical scenario. Okay, so somehow we have to be careful about this fact, because given any two different looking vector potentials, it does not mean that it represents two different scenarios. It can mean that both of the vector potentials represents the same magnetic field and therefore represents the same physical situation. Therefore this chi therefore represents a redundancy of description of a physical situation. Okay, this redundancy is sometimes referred to as the gauge redundancy, and this transformation of a vector field with this the gradient of a scalar, this is known as a gauge transformation. Okay, So now somehow, let's say, we agree to, so we understand that there is this redundancy, of course, because it's clearly, I have exhibited that. Now we have to do something or put a condition so that we fix this redundancy. We need to do that, otherwise we cannot compare. If I ask you that, look, I found in a region, I found this vector potential to be of this form, and can you cross-check this? So you can go, you can try to go and cross-check my vector potential, this vector field, and maybe you find a different answer, different looking answer. Okay, but if we have not made, if we have not gotten rid of this redundancy, then your different answer and my answer could be the same, as well as it could be different. There's no way to say. Just looking at it, if they are different, it doesn't mean that these two answers are different or represent different physical situations. Okay, so in order to compare our results, we need to fix the same gauge, or we need to fix a condition that will get rid of this redundancy chi. Okay, then we can immediately compare, and if your result is different than mine, then we will say that the magnetic field has changed or the physical situation has changed. If your result is same as mine, we'll say that it represents the same magnetic field and the same physical situation. So for this reason, we have to fix a gauge, and this gauge fixing, or we have to fix a condition, and this choosing a particular condition to fix this redundancy is called gauge fixing, or the condition is referred to as the gauge condition. Okay, so now how should we go about doing that? How should we choose this condition? We would like to choose this condition to make our life simple. Remember that the equation for the vector potential had this form, right? The equation for the vector potential has this form. So we see that somehow life will be very simple if this term corresponding to the divergence of A, if this term is not there, because then in that case we'll just have a term which is the Laplacian acting on the vector potential. Okay, so this is the equation that we need to solve to know what the vector potential is in a given situation where this current density is given. So in order to simplify life, we can choose a condition that says this divergence of A equal to 0, and this condition is the gauge condition that fixes our chi. Okay, that fixes this redundancy, that is fixed by putting a condition on the vector potential, and that condition can be chosen to be this condition, which is the condition which says that the divergence of A is equal to 0. This condition can be chosen to be something else also. Again, later on during the course, we'll see that we'll choose this condition to be something else as well. But this fact, is a very good gauge choice, and it's a valid, it's a choice by which we can fix this redundancy, and therefore, we can just choose it and proceed. And basically, we can always choose it. We can show this in the following way, that it is always possible to choose this gauge condition. By the way, this condition has a name. It's called the Coulomb gauge condition. Okay, the fact that the divergence of A equal to 0, this is called the Coulomb gauge condition. And so let's see that if we can always choose this gauge condition and fix the gauge redundancy completely. Let's see if that is possible. So in order to see that, let's say, this is the equation that we need to solve. Let's say again, A1 is a solution. Okay, if A1 is a solution and it is not in Coulomb gauge, so we haven't chosen the Coulomb gauge, maybe we are working in some other gauge. Okay, if this is not in the Coulomb gauge, then the divergence of this solution will not be 0. Let's say that is psi. Okay, because it is not in the Coulomb gauge, its divergence is not equal to 0. If it is in the Coulomb gauge, that is in the Coulomb gauge, end of story, there is nothing to do. But if it is not in the Coulomb gauge, then the divergence of this A1 is equal to, let's say there is some psi. Okay, now if there is this psi, which is the divergence of A1, then we can now do a gauge transformation with a chi, so that A1 is shifted by, this chi. If A1 is shifted by the gradient of the chi, and the divergence of A1 is psi, then we can have a A2, which is minus of the gradient of chi. And if we take this and plug it back into this condition, then we will have divergence of A2 minus Laplacian on chi equal to psi. Okay, and this Laplacian on chi can be brought on this side. Okay, so if we now see that if we choose our chi, given A1, as soon as A1 is given, we know what is psi, and then if we choose our chi such that the Laplacian on chi is equal to minus of psi, then we perform a gauge transformation with respect to this chi, then we can always get a A2 whose divergence would be equal to 0, because if this condition is satisfied, this equation is equal to 0. Okay, so therefore A2 will be in the Coulomb gauge, or A2 would satisfy the Coulomb gauge condition. So even if A1 doesn't satisfy the Coulomb gauge condition, we can perform a gauge transformation using a scalar field which is solved from this equation. Okay, remember this equation is sourced by a psi, and the psi is basically the gradient of the A1, because A1 is not in Coulomb gauge, its divergence is not equal to 0, and that is what we are calling psi. Okay, so given this psi, we can solve for this chi from this equation and do a gauge transformation with the chi, and then we'll get A2 which is in the Coulomb gauge. So it is always possible to choose the Coulomb gauge. This demonstrates it's always possible to choose the Coulomb gauge, and the question that whether or not it fixes the redundancy follows from the fact that this equation has a unique solution given given some boundary conditions. So for instance, if you say that let's say that we are in the Coulomb gauge, and so the question would be that if we are in the Coulomb gauge, then this psi is equal to 0. Then we have the Laplace equation. Okay, and as we know, if we have the Laplace equation with trivial boundary conditions, that is, if we say that the chi goes to 0 at infinity, and we have the Laplace equation which is equal to 0, okay, then basically this will enforce the chi to be 0 everywhere. Okay, so therefore the Coulomb gauge condition in magnetostatics not only can be chosen all the time, but it also fixes the gauge completely because of the uniqueness of a solution to the Laplace equation. Okay, so that is the reason why it is always possible to perform a gauge transformation, that is, find a suitable solution for chi which ensures that the Coulomb gauge condition is ensured, and also it is true, it's not because of the uniqueness of the solution, it's not probably just conversely, but because of the uniqueness of this solution of the Laplace equation, the Coulomb gauge condition fixes the gauge redundancy in magnetostatics completely. Okay, so that is the thing. So it is possible that you choose a gauge condition that doesn't fix the gauge redundancy completely, but that is some condition, and then there is still some redundancy left, and at some point you have to worry about that leftover redundancy and fix gauge completely. Okay, so but the Coulomb gauge in magnetostatics is a very good gauge and will work in this gauge. Very good. Now so let's now see what happens to the equation for the vector potential once we have chosen the Coulomb gauge. So once we have chosen the Coulomb gauge, this was the equation, this was the Ampere's law, right? This was the Ampere's law. So after writing the magnetic field in terms of the vector potential, we wrote down this Ampere's law in terms of the vector potential, and it assumed this form. And now if you choose the Coulomb gauge condition, then this term goes away. This is the reason for the first place why we're looking at this Coulomb gauge condition. Okay, then after this term goes away, then we are left with this equation. And it is very important to note that this equation that we are left with, at least in Cartesian coordinates, are essentially a set of three Poisson equations, right? In Cartesian coordinates, these are exactly three Poisson equations corresponding to the three components of the A vector and the J vector. Okay, So of course in spherical polar or cylindrical polar coordinates, these are, completely different from just, their expression, so the Laplacian on the scalar is different from Laplacian on a vector in spherical polar coordinates or cylindrical polar coordinates. But because the Laplacian acts non-trivially on the unit vectors in those coordinates, and orthogonal unit vectors in the coordinates, there is a non-trivial action of the Laplacian. But if we don't go into make some complicated coordinate choice, if we stick to Cartesian coordinate choice, which is always possible to choose given that all our discussion is in flat space, flat Euclidean space. Therefore, it is always possible to choose Cartesian coordinates in that flat Euclidean space. And once we choose Cartesian coordinates, then this equation, the set of equation reduces to 3 Ponzo equations. And these 3 Ponzo equations we now have learnt in electrostatics how to solve. Okay, we have done we know what the Green's function of this Ponzo equation is, and with the help of the Green's function, the Green's function I mean, if we have the Ponzo equation with delta function source, what is the solution? We know that, and with the help of the Green's function, it is immediately possible to write down a solution for this equation. And we are not going to spend much time there because we have already discussed this once in the electrostatics video. So now we can just take this up and use the fact that we know how to solve the Ponzo equation. And these are 3 Ponzo equations. So component by component, we can write down the solution to the Ponzo equation, which is of this form. Just to remind you that if you are in magnetostatics, then the solution for phi at r, this was given by 1 by 4 pi epsilon naught. Well, the epsilon naught was in the denominator. In this case, the mu naught is in the numerator. Integral of d cube x, some charge density at x divided by mod of this x minus r. So if you remember, this was the result in electrostatics. So in electrostatics, this was the result. Okay, and so this is right. And here we have to solve the same set of equations again, so basically we can do that. Here it's just we just have 3 set of such Ponzo equations, and as you can see from this analogy, if we solve it component by component, this is going to be the same solution component by component. All right. So very good. Now that we have done this, then we have to, we have written down this solution following the same steps as we had done in electrostatics. But in that procedure, there is nowhere, we have nowhere, we cannot assume a priori that this solution also satisfies the Coulomb gauge condition. Okay, because we just solved the Ponzo equation, right? So now there is a question of whether or not this solution satisfies the Coulomb gauge condition, because that was the gauge condition which simplified our equations. And now if this solution does not satisfy the Coulomb gauge condition, then it is inconsistent, and therefore we cannot use it as a solution. So we have to check whether or not this solution that we have written down satisfies the Coulomb gauge condition or not. So in order to do that, here is a very simple trick to see that. You see, so in order to see the Coulomb gauge condition, we have to take the divergence of A and see whether or not it vanishes or not, right? So, but the A, the argument of A is this R vector, and here this X variable or this X coordinate is the argument of the source, and that is integrated over, as is usual in electrostatics as well. Okay, that is what happens, that the source location is integrated over, whereas the location of where you want to find the potential or the electric and magnetic field, that remains as a parameter in this integral. Okay, so that is the usual thing. And now if we take this, and if we want to find the divergence of this, then we have to take the divergence with respect to R, right? So this is essentially, what I have denoted by this subscript r. So what I mean by this r is essentially, this is del r1 I plus del r2 j plus del r3 k, where r1, r2, r3 are the components of the r vector. So this r vector is basically r1 I plus r2 j plus r3 k. Okay, so these are the that is the convention. So basically with this convention we see that we can act with the divergence on this. So if we act with the divergence here, then the divergence will get inside the integral, because this is with respect to r, whereas the integral is with respect to x. So we can take the divergence inside, and also the r variable occurs only in this denominator. So we can write it in this form, that the divergence with respect to r is acting only on this term, which is 1 by mod of r minus x vector. Now we can use this curious identity that if we take this and differentiate with respect to r, and then this is basically the same thing as differentiating with respect to x, or here this Laplacian here, we'll just replace del x1, del x2, del x3, that way we'll just replace this. That is what we mean when we say that the subscript is x. Okay, so the gradient with respect to the r is the same thing as the gradient with respect to the x, with a minus sign here. Okay, so I will encourage all of you to work out the left hand side and the right hand side explicitly and check that this is an identity, that the r derivative or the r gradient can be converted into a x gradient with a sign if it acts on this particular function. It's not always true, of course it's not always true. Okay, but if it acts on this particular function, then this is just an identity, and it can be checked by explicit evaluation of this left hand side and right hand side separately, that these two differ by a sign. Okay, now we will just use this identity in our manipulation. So the divergence of A is given by this quantity, where the divergence is now acting like a gradient on this operator, and then you take the dot with j, because here this dot is with the j here. Okay, so that's why we can take the divergence inside, and the divergence would only act on this one. Okay, it will not act on the j, it will act on the denominator. So now it's like as if there's a gradient, and then the gradient is dotted with the j. Okay, so now in this way of writing it, we can now convert the r derivative into the x derivative, or the r gradient into the x gradient, at the expense of this sign here. Okay, because this identity is true. Now if we do that, then we can take the x derivative, and again this is another identity. Again we have done something like integration by parts. Now you see, with the x derivative, if we act with the x derivative on this combination, now this is the divergence, where this divergence acts on j as well as the denominator x here. Now if we take this divergence here like this, then we will see that there are two terms. The first term is where the divergence acts on j, and then there is another term where the divergence acts in the denominator. Okay, so the divergence, when it acts on the denominator, this will give you this term here, whereas when the divergence acts on j, this is going to give you this term, and the signs are adjusted so that this cancels with this and you are left over with this term. So if you have any doubts, please write this divergence out and check that there's one term that cancels with this one, and you get back this previous line. Okay, please check this. Very good. So if this is the case, then we see that we are in business. You see, because the divergence of j is 0 in magnetostatics, so this term vanishes, we don't have to worry about it. And this term is the divergence of a quantity which is integrated over some volume. Now this volume, if we integrate this quantity over the whole volume, then this current is a localized current. So as long as this current is a localized current, then if we integrate it over a large volume, then that integration would this thing would vanish. So this divergence, again use divergence theorem to write it as this object. Okay, so this we can write using divergence theorem as j divided by r minus x dot ds integral boundary of the volume. Okay, and this would be equal to 0 if j vanishes on this boundary, which is the case if j is localized. Or if you take the sphere at infinity, then it would just vanish because it goes as 1 over x, and because of this reason, this will vanish, okay, if j is localized. So if j is localized, this term you don't need to worry about. This is a surface term, and this is equal to 0. So for localized j, whose divergence is 0, this is going to vanish. So it is ensured that the divergence of our A is equal to 0. So this solution that we have written down, the solution of the three set of Poisson equation treating in Cartesian coordinates, this solution is not only satisfies the vector Poisson equations. This not only satisfies the vector Poisson equations, but it also satisfies the Coulomb gauge condition. Okay, automatically. Okay, we don't need to do anything more to satisfy the Coulomb gauge condition, right? So now, with this, therefore, our magnetostatic problem is solved for any localized current configuration, and this is the vector field corresponding to any localized current configuration, and the corresponding magnetic field is simply given by the curl of this A. So let's see how that goes. So let's take the magnetic field, and let's try to take the curl of this A. So again, when we take the curl, because the argument of A is r, therefore we have to take the curl with respect to the r coordinate, and we can take the curl inside. So if we take the curl inside, then we have to take the curl of this quantity, because we can take the curl inside because the integration is over x. Again, we can take the curl inside. Then the curl now acts on this quantity, but you see the only r dependence is in the denominator. So we can write this curl of this quantity in terms of the epsilon in the following way, that is epsilon ijk, jk, because this is a curl, okay, j and k, this is a curl, okay, and then this derivative is with respect to r, and that is denoted in this superscript here, r. Okay, so this is like, del 1, for instance, here, del 1 here, del 1 r is basically del r1, that's what I mean. Okay, and the r dependence is there only in this term here. So basically we can take the j outside and write the derivative acting on this, and if you work this out, as you can follow the steps here, if you work this out, then you will see that this is basically nothing but, this works out to be, firstly, it becomes minus of 1 over this whole square, and then it acts on this vector here, and then you basically get the unit vector along this r minus r hat direction when this acts on this object. Okay, so you can just follow the steps here. Okay, so you can just take the derivative. You can write this as ri, where there's a sum over index. Now you perform the derivative, so this minus half would become minus 3 by 2, and there's a factor of half, but then there's a factor of 2 because the derivative can act on either of these guys. So it's 2 rj, because the derivative will click only when it hits a non-trivial value of r. So, there'll be a delta ij, ri minus xj, and that is going to give you rj minus xj. Okay, so this is what is going to follow from this action of this derivative immediately, and once this follows, then you can, these two factors cancel, and you can write this as minus r vector minus x vector j, this is the jth component of that, and that is given by, so you can take that and plug it back into this expression here, and once you plug it back into this expression here and adjust the minus sign with, by rearranging this indices, you remember epsilon, this is completely antisymmetric, so if you exchange any of the two indices, you get a sign. If you do the exchange twice, you don't get any sign. Okay, so this is completely antisymmetric in all the indices. So you can rearrange the indices in this way and write this as, eventually you can write this as j cross the unit vector along this direction, r minus x hat direction. So this is the unit vector along this r minus x hat direction, and divided by this is the r minus x hat, that distance whole square. So let me write that down. So if I say that there's this vector r, which is essentially this distance r minus x, okay, then I can write this as j of x, of course, okay, j of x cross this r vector hat divided by the magnitude of r vector square. Okay, so this is exactly what I have here, right? This is exactly what I have here. Okay, so now plugging this back into the integral, as you can see that this is, if I take this and plug it back into the magnetic field which I was finding, so I was finding the magnetic field which is the curl of A here, and that we went inside the integral, manipulated this expression, and we found that this expression, after taking the curl, reduced to this. So we can take this and plug it back into the integral, and this integral was the vector, the integral that was there in the vector potential itself, and we can write down the B in this formula for the magnetic field. For any localized current density, we can write down this formula for the magnetic field, and as you can now identify, this is the same form, and it is called the Biot-Savart's law. Okay, so this Biot-Savart's law is of this form, and we have just derived Biot-Savart's law starting from this Ampere's statement, the local Ampere statement. So basically both the integrated form of Ampere's law as well as the Biot-Savart's law, they originate from the same Maxwell's equation in magnetostatics. And essentially, if we solve that equation completely for arbitrary sources, then we get this Biot-Savart's law, and we get the magnetic field in terms of arbitrary localized sources. Okay, very good. So with this, let me immediately, there's probably a more familiar way to write this Biot-Savart's law, and for that, let me give you a little bit of a mnemonic here. This is a super useful thing to remember, and the idea is that, let's say there is a current density. Okay, so the current density can be an arbitrary object, like it can be any function of this coordinate x, but it can happen that you're talking about a line instead of a current density. There's a current which is flowing along a single line. Okay, so as you know that because it is flowing along a single line, therefore the current density will only be non-zero along this line, and then you can say that the current density has delta function support only on this line. Okay, so the current density clicks only if you are on this line, otherwise the current density is zero. Okay, so because one line can be written by giving two conditions, so it will be like delta of two conditions, and that is going to give you the equation, the equation of a line in three-dimensional space, and those two delta functions you can use here in this expression and integrate them out here in this volume integral to get a line integral. Okay, and this line integral is basically the line integral along the line through which the current is flowing. Okay, so basically you can take anything where there is current density and let's say multiplies anything. It can be a cross, it can be a dot, or any such thing. Okay, it can multiply anything out here, and you can take this and convert it into a line integral over a current by putting in appropriate delta functions here, and this integral then becomes a line integral of a current carrying wire. Okay, so current density becomes a line integral over a current carrying wire. This is the magnitude of the current, and this is the dl direction. Okay, you see the vector direction now is carried by this line integral direction, because this current is moving along the wire. Okay, so this current is moving along the wire, and the magnitude can be written out separately, but this vector integral becomes the line integral, because you have used delta function to focus only on the line through which the current is moving. Okay, so therefore in general you can remember that whenever you have a current density and you have a volume integral of current density, you can convert it into a line integral of a wire through which the current is flowing. So basically current density becomes current and volume integral becomes line integral. Okay, so this is something which is very useful to remember, and so if you do that, so you can recover the result of a current flowing through a conductor directly from this expression by, as I said, by considering delta functions on a line, and that would give you simply, as you can see, there is all these things which are part of this dot dot dots. And then if you have the delta function here, it will only click where the current is non-zero along a line integral, and that is going to give you this line integral here, and that will be crossed with the same things that were there before. Okay, so you remember that this vector index is now borne by the line integral vector index. Okay, so this is a very interesting thing, and maybe in many places the Biot-Savart's law is stated in this way in terms of a current conductor, because current wire, okay, which is a line integral. Okay, so but in general this is a volume integral, and in general this is a current density, but only in the special case where the current density is a current carrying wire. So basically in that case you can use the delta functions and localize on the wire and convert this integral into a line integral. That's what I'm saying. Very good. So now once you have this, then basically you can also play the same game for the potential. You will learn that the potential for a localized source is given by J. This localized current source J, current density, and taking that and integrating it over volume V, that gives me the in this way, if I integrate it, that gives me the vector potential. I can also now convert it into a line integral and take the current out, and this becomes the line integral under the same mnemonic, under the same kind of thing. Okay, we can write down the vector potential due to a current carrying wire. This will be the expression. By putting in appropriate delta functions in this current density, we can land onto this expression for a current carrying wire. Very good. And usually this, because the current carrying wire has to be a closed circuit, so usually this is a closed line integral. Okay, here as well as here. So usually this is a closed line integral because the current carrying wire has to be a closed circuit. So in realistic practical cases, this is a closed line integral. Okay, so that brings us to the end of this discussion about vector potential and its general solution. So this is what we have seen in magnetostatics. We can somehow solve the so this is somehow we have seen in electrostatics as well, that we can solve the electrostatic problem completely for an arbitrary localized charge density. And even in magnetostatics, we see that once we have introduced this vector potential, we can solve the magnetostatic problem completely for an arbitrary localized current density. Okay, that we are seeing here. Very good. So with this solution, now we want to play the same game as we played during multipole expansion in magnetostatics, in electrostatics. So in electrostatics, now we wanted to know that, let's say there was a localized charge configuration, and what is the form of the potential and the electric field far away from that localized charge configuration. Okay, now here also there is a localized current density or localized current configuration, and far away we want to check that we want to see that what is the form of the vector field or the electric or the magnetic field. Okay, we want to see what is the form. Okay, so this can be done by doing a similar kind of an expansion as in electrostatic, and it's called the multipole expansion in magnetostatics. Okay, so before I proceed, let me mention one point which I kind of missed saying before, and this one point is, you might wonder why or how this current, this current, we are saying that there is a steady current, but there is no charge density. Okay, as I said, there can be static charge densities as well, and we'll solve the the electrostatic problem separately. There can be static charge densities, but in general, when, let's say, current is flowing through a wire, generally there is no charge density, but there is a current density. And the reason why that happens is, in the wire, let's say, some electrons are flowing, resulting in some current, but these are flowing in the background of some positive charges. And therefore, there is overall charge neutrality, to a great extent. And basically, in this situation where electrons flowing through a wire, for instance, in this situation, you can clearly see that there can be a non-zero current density, but zero charge density. Okay, so that is possible. And so this was a comment I should have made in the beginning of the magnetostatic ansatz. But very good. So this is the thing that the realistic scenarios are scenarios which represents magnetostatics. There we have current flowing through wires, and there in that case we can realistically forget about the electric field. Of course, if we go very close to the wire, there will be electric field because there's some kind of charge separation after all, and some higher order multiple moment would be non-zero, and so that is why you have to go very near to the wire to measure them. But if we are far away from the wire, then it will have a magnetic field because there is a non-trivial current flowing through it, but it will never have any electric field. Okay, so that is what we are seeing here. Now, before going into the more complicated scenario, let us consider the simple thing first. Okay, let us consider this tiny little loop here. This loop, which is like, it can be a circular loop as well, through which current is flowing. And so one point in this loop is given by this x vector. Any point on this circular loop is given by this x vector. This circular loop is denoted by C, and there is a I current, steady current I, which is flowing through this loop. And again, this is a localized source because inside this region the current density is localized, and I am interested in the magnetic field or the vector potential far away from this localized source. Okay, this is what I am interested in. Now we know that what is the potential due to this loop. We have solved the problem generally. Okay, the potential due to this loop is basically this line integral, where C is the loop about which the current is flowing. Okay, so if that is the case, then we have this denominator here, and we are interested in the far region, okay, where the mod of this R is, this far region is essentially this mod of R is much greater than this mod of X. Okay, the radius, typical radius of this loop, let's say. Okay, the point where I'm interested is very far away from the location of this current distribution. Okay, so under that assumption, again we can take this and do like a Taylor series expansion like we did before, and I'm keeping just the first term here. Okay, the first two terms, the leading order piece and the first non-zero piece here. These two terms we are keeping, and then there are higher order terms which are there. So again, in the electrostatic case, this corresponded to total charge. This term corresponded to the dipole moment, and there were quadrupole moment, octupole moment, and so on. But in the magnetostatic case, we are not worrying too much about the quadrupole moment, etc. Okay, so if we have this this expansion and we plug it back into the expression for the vector potential, then let us see what happens term by term. Okay, so if we take this first term, then we see that the first term is essentially, we can take the R 1 over R outside the integral. So what will be left over is this line integral of a vector, this vector line integral of a closed loop. The vector line integral of a closed loop is always zero, because you can just take a closed loop. And if you have a area, a little bit of a element here which is pointing in this direction, and if you consider, this thing would be cancelled off by, for instance, a little bit of an element here pointing in the opposite direction. And therefore, if you do this for all the area elements, vectorical addition, vector addition would give you zero. If it is not a vector addition but just a loop, this thing, a loop integral without any vector, then you will get the circumference of this loop. But if it is a vector integral, then this vector integral essentially is essentially zero, and therefore this term vanishes, because this is a vector integral over a closed loop. Okay, vector integral over a closed loop must vanish, so this term vanishes. And now, so this is essentially, therefore, we are seeing that in general for this particular configuration, there will be no term corresponding to the charge. Okay, so this is similar to the dipole that we have seen in electrostatics. We saw for the dipole, the total charge was zero. So the first term, or the first dominant term, started from the next term in the multipole expansion, and it had a non-zero dipole moment, and it therefore gave us this thing. So at least for this current configuration for the loop, we see that the total charge term, the analogous term for total charge in magnetostatics, that term is 0. At least that we can see for this current carrying loop kind of a thing. Okay. So, but what happens to the next term? This next term, therefore, you can see that this is r dot x. This term is r dot x vector divided by r square. Okay. And of course, there are higher order terms which we are not caring about at the moment. But if we take this term, r dot x vector, then this term can be written in terms of two cross products. This term can be written in terms of two cross products. If you want to see this, you just write this out, this cross products out in terms of the epsilons, and then you will see that this identity is just valid. You can see this as follows. Okay, okay. Let me. Give me a moment, I'll prove this identity. Okay, but if this identity is true, then you can see that, this part here, half of this thing, this is nothing but the area of the loop. Okay, it is the area of the loop, and it is the area of the loop cross R. Okay, why is this the area of the loop? Because we have a closed loop here, and if we take, this half into this x, so x is this vector, okay, and let's say, maybe I should have written x is this vector, x is this vector, and then dx is basically this vector, then x cross dx, half of that is basically the area of this triangle. And now if you do it for this whole loop here, then you will get basically the area of this whole loop. This integral ds, this is basically the area of this whole loop, area enclosed by the whole loop, and this is basically pointing in one direction, which is determined by the direction of the flow of the current, right? So this essentially, therefore, this term here is nothing but the area, and its area vector cross r hat vector, and so basically this term, therefore, x dot r term can be written as the area vector cross r hat vector. Okay, that is the thing. But let's see now if we can show that this result is valid, where this dot can be written as two crosses. Okay, can we do that? So in order to do that, or can we do that, or when can you do that? In order to do that, let's go through these steps here. So let us say that we have some constant vector g, and multiply the constant vector g on this side of this. So basically this is like a line integral x dot r hat. This is a vector. So we'll take a constant vector g and dot it on this side. Okay, so if we dot it on this side, then we'll have an expression like this, where g is a constant vector, arbitrary but constant vector. That is the thing. Okay, g is an arbitrary but constant vector. Now we can take this expression and take g inside and dot it with x hat. That is very clear. Now once we dot it with x hat and dot it with x dot r hat, then we can essentially say that this is x vector dotted with g times this quantity. Okay, so if this is x dot, so this is the closed line integral of a vector which vector is g vector times some scalar, and this scalar is x vector dot r hat. Okay, so then we can immediately apply Stokes' theorem and say that this is the surface integral now, surface integral of a surface which is enclosed by this C, curl of this vector. Okay, that is essentially true by Stokes' theorem. Okay, so now if we take this object where, of course, this curl is to be taken with respect to the x. So this x is the x coordinate here, and this is the x coordinate with respect to which the curl is taken, because we have applied the Stokes' theorem in this, assuming the loop, this is x, right? So this is the x coordinate. Now, if we write this curl out, so using the epsilon ijk symbol, then this derivative is basically this del j with respect to x, xm r hat gk. Okay, that's just writing this out in terms of components. And then this derivative acts on only on this xm and gives us a delta jm. Okay, the derivative gives us a delta jm by action on xm. And this delta jm essentially after, there's this j index here and this, right. So, okay, so there's this m index here in this r as well. So we perform the sum over m and this r hat gets the j index. And now j is also summed over, I is also summed over. And this is the free index which is dotted with the g vector here, and because g is a constant vector, now I can take it out again. So if I take it out, then this is again g dot integral of the surface vector, this ds vector, infinitesimal surface vector, across this r, because this is exactly what that is, because this is the cross product in terms of the epsilon, right? So now this ds, again for the reasons which I just explained, can be written as half of x cross dx, and this is the surface vector here, and cross r hat. Okay, so and this expression, as we can see, g played a very important role in the manipulation, but eventually this one is equal to this thing for an arbitrary constant vector g. Okay, for any arbitrary constant vector g, this is true. In general, you can choose this to be your unit vectors along ijk in Cartesian coordinates, and then basically this would imply that this vector should be equal to this vector as a vector equation. Okay, so that's why we have this vector equation, which basically says that this thing is equal to the area across this thing, and this is the explanation that I gave you above. Okay, that this is the area, and this area can be written as half of x cross dx, where this is x and this is dx, and this is the area. Okay, so very good. So this is the this is our conclusion. So now let's look back at what we had. We had the area, the vector potential given by these two terms and plus higher order terms. The first term vanished because of the vector line integral of a closed loop, and the second term we are analyzing, and the second term, using this identity that we just derived, can be written down in this form, where it's I times the this integral can be written down as the area integral cross r. And so basically you can take the I and multiply it with the area, this area vector of this surface, and this together, this quantity is referred to as the magnetic dipole moment of the current carrying loop. This you may have seen before. So this is the current magnetic dipole moment of the current carrying loop. So in general, if we denote this by m, then we can write the potential in the form, the vector potential, as mu naught times m cross r divided by r cube. Sorry, this is, if I write r square, sorry, if I write r vector, this is r cube. If I write r hat, this is r square. Okay, so maybe it's better to write it in terms of r square and write this as r hat. That may be better actually. That makes the r dependence manifest. Okay, so again, this is some quantity where we see that the vector potential goes as 1 over r square. It's very similar to the scalar potential for the dipole, that also went as 1 over r square. But now this is a vector, so you take for the case of the scalar potential, you took the electric dipole moment and dotted with r hat. But because this is the vector potential, you have to take the magnetic dipole moment and cross it with r hat, so that this is also a vector eventually. Now, as an exercise, this will be a very important exercise, and I'll give it to you in your problem sets as well. So you need to find the magnetic field corresponding to this vector field of a dipole, and then match this magnetic field or compare this magnetic field with the electric field of a dipole. Okay, compute both the things. You know what is the scalar potential for a dipole, you know what is the vector potential for a magnetic dipole, and then compute the corresponding electric and magnetic fields in the two cases and compare your result. I'm leaving this as an exercise for you guys to do. Okay. So good, that brings us to the, so we have discussed the dipole. Now let's do it slightly more generally. Okay, let's do it slightly more generally. So let us consider the, instead of considering one current carrying conductor, let us consider a general current density J. Okay, let us consider a general current density J. And if we consider this general current density J, then here also we are interested to play the same game. Let's say there is a localized current density J in some region, and we are interested in the vector potential far, far away in the far region, where again this far region is denoted by this condition. So there again we can do the like the Taylor series expansion first, and after we do the Taylor series expansion, we can take it and plug it back in here for this term here in the denominator. We can plug it back in, and then we see we have these two terms, leading order two terms, plus there are higher order terms which will not care in the magnetic case for the moment. Okay, now we see that the first term, last time we saw that this was a line integral of a vector. You know that happens because again if you remember the mnemonic, then this becomes a dx vector, and then we multiply by the current, and this is a closed loop line integral. Okay, so that was the closed loop line integral that was equal to 0 in the previous case. But here we have the divergence, here we have the current density. It's the volume integral of the current density that is there in the first term, and in the second term there's a xi times current density times dx cube. So these terms look very different compared to the case that we just handled. But so this is a one step more generalization than just a single current carrying loop. There can be a complicated structure of the current, and this will be a general multipole expansion for a general localized current density. Okay, this is the exterior multipole expansion, if you like, for a general exterior magnetic multipole expansion for a general localized current density. And we are interested in the vector potential far away from that localized current density, and we want to find what is the magnetic field. Finally, when we know the vector potential, we can take the curl of it to know what is the magnetic field. Now let us see how to proceed, with these two terms. So the first thing that we notice about this term is the volume integral of the J we have to perform. So in order to simplify this first term, what we do is we consider this following identity. Okay, this following identity says that it's the volume integral of this whole thing, three terms, 1, 2, 3. This volume integral should be equal to 0. That is an identity. Okay, why is that an identity? It is an identity because if you take the divergence of this vector, f and g are scalar functions, arbitrary scalar functions. If we take arbitrary scalar functions f and g, multiply it with this current j, okay, then this is a vector. And if you take the divergence of this vector, then you see term by term you will get these three terms, because this divergence will act on f first, then this divergence will act on f first, then you get basically this term. If the divergence acts on g, then you get this term, and when the divergence acts on j, then you get this term. Okay, so term by term this is reproduced if you write the divergence out here, but it is the volume integral of a divergence that can be converted into a surface integral of of this quantity, of this vector here. And if j is localized, then you can always consider this surface which is larger than this, or you can consider this volume which is larger than the region which contains the localized current densities, and therefore the current density is going to vanish on the surface of this volume. And because it vanishes on the surface of the volume, on S it vanishes, then this integral should vanish. Okay, so basically this is an identity which is true if we have localized current sources J. Okay, so if this identity is valid, then we look at one of the terms of the identity. This has the divergence of J, and we know that in magnetostatics divergence of J is 0, so this term is 0. So with this term 0, we land up with this identity. We land up with this expression. So in general, we have this expression here, which unfortunately I have not written down. Let me write it down. Right. So I will just write down this expression. So if this is 0, then there's a step in between, and I can write this as, so this integral d cube x f of x j dot grad on g of x. Right, that's the first term. And then there's just one more term, g of x j dot grad on f of x. This is equal to 0. Because this term is equal to 0. Firstly, this whole three terms is equal to 0 because of this reason that I explained. And then one of these three terms is 0 because divergence of j is 0. And therefore, we are reduced to these two terms. Now, in these two terms, if I choose, because f and g are arbitrary functions of x, y, and z, or x1, x2, x3. They're arbitrary functions of x1, x2, x3. You know, this f and g. And if we take this identity for divergence of j equal to 0, this identity is valid. If j is localized and if divergence of j is equal to 0, then this is a valid identity. And if we take this identity and set f equal to 1 here, and g equal to x1 here. Okay, so x1, x2, x3 are the coordinates. So we can set g equal to x1. If we set g equal to x1 and f equal to 0, so if f equal to 0, if f equal to 1, then this term vanishes. Okay, this is the 0. And if g equal to x1, then this is going to give me just my one component of j, or x1 component of j. Okay, because you know this is the only component which will not be 0. Okay, if g equals to x1, then only del x1 will be non-zero and everything else, all the other terms will be 0. So this will give me the x1 component of j. Okay, so we see that the x1 component of the volume integral of that is equal to 0. You know, just by making a choice, you know, by making this algebraic manipulation using this identity, we see if the divergence of j is 0, then the volume integral of the x1 component of j is 0. So similarly, we can choose g to be x2 and x3 and show that the x2 component and the x3 component should also vanish. Therefore, this vector, you know, this as a vector, therefore, the volume integral of the current should vanish if the divergence of the current is 0, which is something which went in non-trivially. If the current is localized, you know, this condition has gone in, that it's a localized current. And the second condition that has gone in is this condition which is true in magnetostatics, that the divergence of j is equal to 0, that has also gone in. These two conditions together, you know, tell me that the volume integral of this current must vanish. So the volume integral of the current, if it vanishes, looking back at this expression for the vector potential, we see that this first term vanishes for an arbitrary for an arbitrary current density, this term vanishes. So we see in magnetostatics, there is nothing that corresponds to total charge. Okay, so there is nothing that corresponds to total charge, and the multiple expansion starts from the dipole term. We saw that this term can be non-zero for a current carrying loop. You know, this term, this subleading term, but this leading term, this 1 over r term in the potential, that is identically 0 in magnetostatics, because the volume integral of a current whose divergence is 0, of a localized current whose divergence is 0, that volume integral must vanish. And therefore, we don't have any, magnetic charge, any notion of total magnetic charge for an arbitrary current distribution. We don't have any notion of total magnetic charge in magnetostatics. Okay, so let's look at the second term now. Let's look at the second term. So the second term can also be processed in a very similar fashion. Right. The second term can also be processed in a very similar fashion. Yeah, again, going back to this identity, the same identity that we used in the previous case. So the second term has this form, as I wrote down here. There's a xi. This I index is contracted with r. So this is basically r hat dot x vector. This is the term. And then there's current density and the integration over x vector. So I can take the r hat outside and write r hat divided by r square. And within the volume integral over the source, So there is a xi that multiplies it. You remember, just to remind you, the dipole moment of an electric charge, that dipole moment vector p is equal to integral, it's a very similar thing, xi rho x d cube x, right? So that this was the dipole moment of a electric. So this was the dipole moment, electric dipole moment, right? So the electric dipole moment for a charge density, the electric, just to remind you, electric dipole moment that was given by this p vector. This p vector is equal to this integral of this x vector rho of x vector d cube x. Okay, so for a given charge density, this was the electric dipole moment which we had seen before in electrostatics. But now in magnetostatics, you see the expression that we are left with here has this form. It has a very similar form, but you see there is this vector index here, as well as there's a vector index here, as well as j carries a vector index which corresponds to this. You're talking about a vector potential here. So there has to be three terms, but those three terms are multiplied with the xi. Okay, those three terms are multiplied with the xi. Now let's see if we can manipulate this expression and write it in a slightly more compact form. So again, we go ahead and use this identity here, which is this identity, and we can set this part to 0. Okay, these two terms to 0. And in those two terms, now if we choose f is equal to x1 and g is equal to x2, then we get this identity x1 j2 x2 j1 equal to 0. Okay, so similarly choosing, now choosing f equal to x2 and g equal to x3, we will get, x2 j3 x3 j2 equal to 0, like this. So in general, by choosing f and g judiciously in this identity here, we can basically show that xi jj and xj ji, that is basically equal to plus this thing, that is basically 0. And basically if we symmetrize, that means I and j, if we interchange, then that expression should have a minus sign. Okay, so this can be written down as this expression should have a minus sign. This volume integral d cube x xi jj is equal to minus volume integral of xj ji. Okay, that is the conclusion that we draw from using various choices of f and g. Just choose x1 x2, and then you can choose this to be x2 x1 and so on. Okay, you will see that this identity would always be true. Okay, by making such choices in this expression here, in this identity which we have argued to be true just a while ago. Okay, so if we now try to use this, so let us try to see. So xi xj we have, then we can write it as twice of this xi xj. So we have divided by this factor of half. Now if we can use this identity here, okay, we can use this identity here and convert this xi xj into xj xi, but then I'll get a sign here. Okay, now if I get a sign here, then I can package it and write it as half epsilon ijk x cross j, because this is the kth component of this, which is contracted with this epsilon. Because if we write this out, why is this true? I have explicitly worked it out here. So we can write this out in terms of the epsilon. Now there's a common index k. Because there's a common index, we bring the common index in front just to say that we are in the same sign convention. There's no minus sign. And then we can write it in terms of 2 epsilon in terms of the deltas with one index contracted. And once you write this in terms of the deltas, we see that this becomes xi xj xj xi. Okay, this term therefore can be written as x cross j kth component. This kth component is contracted with I and j, and this ij was basically this term to begin with xi jj. Okay, so this is like has two indices I and j, and this also has two indices I and j. Therefore, we can write down this identity that we just derived with I and j. These two indices, free indices are there, and this k index is contracted with this k index, and this is can be written as x cross j. Okay, this is just some algebraic manipulation. Okay, so if we substitute this algebraic manipulation back into this expression here for the vector potential, then xi xj, this we can write as epsilon ijk, x cross j, and then using this fact again that there is one epsilon, we could write this as m cross r hat divided by r squared. Is exactly the same expression that you got for the dipole moment of a current carrying loop. And basically here for a generalized charge, basically m is defined in this way that it is x cross j, and the volume integral of that, this can be non-zero for a non-trivial charge, and as you can see for a current carrying wire, this is non-zero. And this is the general definition of the dipole moment. So given any current configuration, any general current configuration, you should be able to take this expression and calculate this cross product and then integrate it to find what is the dipole moment of this general current carrying, general current configuration, general localized current configuration, which is divergence free. This is the magnetic dipole moment of that current configuration. Again, if we just apply the mnemonic, then this j would become the line integral of a closed loop, and then we'll recover the previous result as we had before. It's I times the area vector. This was something which we had before using this kind of a mnemonic that we discussed a while ago. So basically this becomes, this m can, for a current carrying conductor, this m is basically I times the integral of the of the area enclosed by the current carrying conductor. But in general, for a general charge, general current distribution, in general, m is given by x cross the current distribution and the volume integral of that. Okay, again, I'll give you some exercise so that you can, in examples, work it out. Also, even beyond my problem sets, you should try to take various current carrying, conductors or various configurations with, localized J and in magnetostatics, and try to evaluate the magnetic moment corresponding to that configuration. For instance, if you take a charged sphere and if you start spinning it, then can you compute the magnetic dipole moment of that spinning configuration, for instance, okay, using this formula. Okay, so that could be one of the things that you can try to compute. Okay, of course, that would also involve magnetostatics, because there will be well, it's not really statics, it's a constant angular velocity. If there's a constant angular velocity, then everything is not static, it's a stationary configuration. And if it is completely charged, then there will be electric fields due to the charge as well. But in that example, you can imagine, you can just focus on the magnetic dipole moment of that configuration and try to find out what the magnetic dipole moment is. Okay, I mean, similarly, I'm just encouraging you to practice a lot of problems where you find the magnetic dipole moment of a given current configuration. You find the magnetic dipole moment, and once you have found the magnetic dipole moment, we can immediately compute the vector potential. And as an exercise, you are going to compute this. I have left it as an exercise. As I said before, given the vector potential, you can try to find what is the magnetic field corresponding to this magnetic dipole moment, and that can be found, and that can be compared with the formula for the electric field for a electric dipole. Okay, so that is what you are going to do. And but the main thing is this formula, that for general charge distribution, for general current distribution, the main thing is this formula. For general current distribution, steady current distribution, the m or the magnetic dipole moment is given by x cross this thing. That is the main thing that came out of this multipole expansion. Of course, you can go to one higher order, trying to write down what a magnetic quadrupole would be. And this, for instance, can be a topic in your essay. Okay, you might want to work it out and flesh it out. Okay, the magnetic quadrupole moment, and that can be a very nice exercise if you want to like just get your if you want to get your get the calculations up and running. Okay, so very good. So that is all I have to say about the multipole expansion topic in magnetostatics. Before finishing before quitting this topic, I want to discuss one more item here in case of magnetostatics. This we could have also discussed in electrostatics, but I preferred discussing it in magnetostatics and then giving the electrostatic problem as an exercise. Okay, that is a good exercise whether you are understanding this. So basically what we are going to try to find here is the magnetostatic force on a localized current distribution when there are some external magnetic fields. So there is a localized current distribution like this, and then there is some external magnetic fields which are slowly varying. They are varying magnetic fields, but they are slowly varying. Okay, I'll explain what I mean by slowly varying. And so this current distribution will experience a Lorentz force in this magnetic field, and the question is, what is that Lorentz force for this localized current distribution? Okay, so that we want to figure out. Now, I must say that you can ask a very similar question in electrostatics as well. You have a given current configuration. You have a given charge configuration or charge density in electrostatics, and you put it in some non-uniform electric field. In electrostatics, you have a non-trivial charge configuration, and you put it in a non-uniform electric field. Then you can ask whether or not that experiences any net force. And the kind of calculation that we are going to do here would be very similar in electrostatics as well. And you are encouraged to find that force, solve that problem. I'll give it to you in your problem sets. But here we'll discuss the magnetostatic force on a localized current carrying distribution. And then we'll leave the corresponding electrostatic problem as an exercise. Okay, so now before starting, let me immediately say what are my assumptions. I would assume that the magnetic field is slowly varying. What do I mean by that? I mean that the variation of the magnetic field is not appreciable, that the magnetic field doesn't change much as far as the typical length of this current carrying distribution is concerned. So let's say the current carrying distribution is like this. It is enclosed within a sphere of radius r. Then we'll say that this magnetic field doesn't change appreciably over length scales of distance r. Okay, over length scales of magnitude r, the magnetic field doesn't change appreciably. So this is what we mean by slowly varying. The magnetic field is slowly varying compared to the dimension of the current configuration. Okay, so under such an assumption, we can choose our origin of our magnetic field, origin of our choice inside the current carrying conductor, and we can try to find the total force on this current carrying, current configuration. What is the total magnetic force on this current configuration that we can try to find. Now, as you know from the Lorentz force condition, this is given by J cross, this is the force density as we discussed in the beginning of the video. So this is the force density. We can take the force density and we can integrate it over the whole volume where this current density is not zero, and we can find the force on the current density due to some external magnetic field. Okay, so this B can be some external magnetic field, not only the magnetic field produced by the current density, but it can be some external magnetic field which is exerting some force on some current carrying conductor or some current distribution. Okay, so in this scenario, we said that we are going to take this slowly varying assumption. Okay, we assume that the magnetic field is varying slowly. Because the magnetic field is varying slowly, therefore we can do a Taylor series expansion of the magnetic field about the origin. Okay. Before doing that Taylor series expansion, let me mention one very important point. In this expression, when we do this integral, take this force density and we do this integral, then what we are doing here is we are basically finding a vector sum of all the forces acting on the current configuration. So let's say the current configuration is something like this, and there are various forces acting at different points on this current carrying this current configuration. We are taking all these vectors and doing a vector sum of all these vectors. This is what this integral does. Okay, and so this is the net force which is acting on the current on this current configuration. So let's say you want to write down some kind of a Newton's law for this current configuration. Then you can say that the mass of the current configuration is concentrated at the center of mass, and there is a total force like this which acts on the center of mass. And then with the help of this total force, you can write down some Newton's law for this current carrying configuration. Okay. So you should think of this as a vector sum of all the forces, not like a force acting at a single point. Okay. So for a current carrying configuration, various points are affected by different magnitude and direction of force, and you take that and do a vector sum of it, and you get this result. Okay. Well, that is important. So that is the idea when you know what kind of force you are calculating. Okay. So now if we do that, if we have that idea in mind, then we can take our magnetic field, which is slowly varying over the configuration, and do a Taylor series expansion of it in the following way, that we want to expand the magnetic field about the origin, and we can choose our origin, let's say at the center of mass or at the center of charge here. Okay, and we can work with that choice of origin inside the conductor. And then the magnetic field is slowly varying with respect to the length scale of the current configuration, and therefore, if we have this B, if we have this B, which is this is the magnetic field at the origin, and this thing is because it involves derivatives and it's slowly varying. The second term involves derivatives and is slowly varying. Therefore, the second term is subdominant compared to the first. And similarly, the higher order terms are all negligible under this slowly varying assumption, because the higher order terms should contain higher and higher powers of the derivative. And if it is slowly varying with respect to this, configuration of interest, then we can ignore these higher order terms safely, and we'll just keep the first two terms. Okay. If we keep the first two terms and plug it into the expression of the force, then what do we see here? We'll see that again, the force will have the two terms. The first term will again be an integral of the current. You see, if I write it down in terms of this cross product in terms of the epsilon, using the epsilon, then we'll see that this becomes component by component for J. This becomes a volume integral of the current J. Again, because the J is divergence-less and it's a localized current distribution, therefore this term is going to vanish. Okay, so this first term, this B naught, will have no effect no force will be exerted because of the leading term in B naught when we do the Taylor series expansion. So only if the magnetic field is varying and there is a non-zero the derivative on the magnetic field near the conductor, if that is non-zero, only then the current carrying configuration can experience a force. Otherwise, if we have constant magnetic field where all these terms are zero, then this term would simply vanish and there will be no force. Okay. So constant magnetic field will not work. The magnetic field has to be non-uniform for the force to be non-zero. Okay, that's the first lesson. And then from the second term, we see that the second term we can write as, here, we can write this second term, this J, I'm writing it, this cross product, this I'm writing out with respect to the epsilon symbol. And so if we do that, then there is a J which is here, this J is contracted, this K is contracted, and this M is the free index M, which is the M index of the force. So the force is a vector, so it has an index, and that is the M index of the force. Okay. So basically, the first term goes to zero. So if we just retain the leading order piece, then this leading order piece has this form that we are supposed to take the derivative of the magnetic field and set that to be equal to zero, because it's a Taylor series expansion about x equal to zero. So we are going to set that to zero. And this is what we mean, that we are going to set this to zero in this derivative, and then we are left with xi xj. Again, we know xi xj can be written using this identity epsilon ijk. This is the identity we derived and used a while ago in the multipole expansion. Using this identity, we can again write down this xi xj term in terms of x cross j, and using the corresponding epsilon here. So we are using this identity in here, then we get this term. Okay. Now if we just keep track of where the indices are and do some rearrangement with the indices, then we see that this term essentially, along with this factor of half, this is basically the magnetic dipole moment. Okay. So because this is the magnetic dipole moment, so I'm writing it as m. This is the magnetic dipole moment of the configuration. And therefore, this force, the leading order force, therefore, would be proportional to the magnetic dipole moment of the charge configuration. And if we write this epsilon out again in terms of the delta, okay, because there's one index which is common, then we can write it in terms of the delta. Then we can make this term, we can take this and write this into two terms. One term which is proportional to the divergence of B, and by Maxwell's equation this is 0 because it's the divergence of B. And then there's another term which looks in this like this. Okay, if I write it like this, it looks like this. But as you can see from here, this n index is contracted with the n index here, but m is independent of x. So you can take this inside the derivative. It is an integral expression. It's just some some constant vector. So you can take this inside the derivative, and you can write it as del m acting on b dot m. Okay, in general, and this divergence of b just goes to 0. Okay, so therefore the force reduces to the divergence of b dot m, where the x dependence is contained in here. Okay, so basically you can once you have obtained this expression, then you can think of this as a force field. There's a magnetic field, and there's a magnetic field, and there are magnetic dipoles, and at various points in the magnetic field, the magnetic dipole experiences various forces, which is given by the divergence of the magnetic field dotted with the dipole moment, and we take the gradient of, take the magnetic field and dotted with the dipole moment, and we take the gradient of that. Once we take the gradient of that, that gives us the total force acting on the dipole. Okay, that's the vector sum of all the forces acting on the dipole. Again, let me emphasize that this is the leading order force on the charge configuration. There can be sub-leading order corrections to this force. If the magnetic field is strongly varying, then there can be quadruple corrections to this force as well. Okay, so the leading order force for a slowly varying magnetic field is given for any arbitrary charge configuration, for any arbitrary current configuration. There can be, the leading order force is proportional to the magnetic moment of the configuration. And of course, that configuration can also have non-zero magnetic quadrupole moment, etc., etc. Okay, and those can also be, those can also experience force because of those moments. But for the leading order for slowly varying magnetic field is proportional to the magnetic dipole moment. Okay, so that is what we have. Of course, if you are given a loop of wire which just has a dipole moment and all other moments are 0, in that case, then this is the force that the loop of wire will experience in a non-uniform magnetic field. Here you have to remember that for this to be non-zero, the magnetic field has to be non-uniform, because that is what gets the x dependence. So you take the derivative and act on the x dependence here, and then set x equal to 0. That's what you are supposed to do. Okay, x equal to 0 being the location of the magnetic dipole. Okay, so that's what you are supposed to do here. And so basically, therefore, as I said, you can treat this like a force field in which magnetic dipoles are moving around, and depending on the location, you can convert now this expression into a force field which is present at every point in a force that this magnetic dipole experiences at every point in space, given that there is a non-uniform magnetic field there. Okay, again you can think of this in terms of a potential. This force on the magnetic moment is also conservative, in the sense that of course Coulomb's law we have seen, that kind of force is conservative, and this force is also conservative, that we can write it as the divergence of some kind of a potential, and that potential is nothing but the magnetic field dot the magnetic dipole moment of a current configuration. Okay, so a current configuration with a non-zero magnetic moment will experience a force and the potential for that force is given by B dot M, or minus B dot M rather. This is again a sign convention, the usual sign convention. So this is given, this is there, and so basically for non-uniform magnetic field, the current carrying conductor can experience a force. Okay. So now the question is, so if you put a non-trivial, there's an interesting question. So if you put a non-trivial loop in a non-uniform magnetic field, then it will experience some force, right? Now if it experiences some force and it moves, then somebody does work. But as you all know, that magnetic fields do no work because it's a V cross B force, and if you take a V cross B force and try to find work, then it is like, V is dr dt cross B dot dr, and this term, identically vanishes as a vector identity, and therefore the work done must be 0. So as long as the magnetic force is V cross B, by the way, we have used the V cross B force to derive this in the first place for the dipole moment. This expression has gone in non-trivially into this expression for the force, and once we have derived this, we can ask that if this loop moves, who is the person who is doing the work, because we know that the magnetic fields can do no work because it's a V cross B force, right? So as you, I think many of you know that this work is being done by the agency that drives the current in the loop. So let's say we put a loop with a non-zero magnetic, current carrying loop with a non-zero magnetic moment, and then it experiences a force in a non-uniform magnetic field, and this force makes it move, and this motion is essentially the work for this motion is done by, let's say, the battery, which allows the current to flow through this, or which forces the current to flow through this loop, and thus give it a non-zero magnetic moment. Okay, so therefore the magnetic field is not the one that is doing work on the system, but it's the battery that is doing work. And so this is what anybody would tell you, and if you read Griffiths, this is what Griffiths is going to tell you. Now what I'm going to do is I'm going to leave you with a little bit of a puzzle, because there's something interesting to think about here. The point is whether this expression we have derived from the V cross B force, but there are objects in nature like the electron itself, which actually not is a there is no current carrying loop or anything like that, or there is no battery inside the electron, but it has a non-zero magnetic moment. Okay, so if it has a non-zero magnetic moment and you put it in a non-uniform magnetic field, it will experience a force like this. Okay, although the derivation here that we gave would not work, but also because this is probably not within the classical domain. The fact that the electron has a magnetic moment, this is essentially pertains to the domain of quantum mechanics or quantum field theory rather, and therefore probably this is not to be treated classically, not to be thought about classically, but it is a one can think of this classically as well, as because once the magnetic moment is generated, the electrodynamics part is classical, and you can experience a classical electrodynamical force. So there is an electron with a magnetic moment which is not generated by a battery, and if you put it in a non-uniform magnetic field, it is going to experience a force given by this formula. And then the question would be, then who is doing work in that case? Okay, so that is something to think about. Who is doing work in that case? That is something to think about, and I will leave you with that thought. Okay, I will leave you with that thought. I want you guys to explore this question and see if you can find a good answer to this question. Search the internet, go everywhere and see if you can find a good answer to this question. And I'm going to leave you with this question. Okay, I'm going to leave you with this question, and I'm also going to give you a few exercises. This will again come out in your problem sheet. So the first exercise would be to define something like a torque density. You know that this was the force density that we defined. If we take the force density and do the cross product with x, that defines the torque density. And if we take the torque density and integrate it out, then we'll get the total torque, or the vector sum of the torque that is acting on the system. And then basically I want you to take this torque density and integrate it out for a general current distribution, and I want you to show that the torque on the system is given by the magnetic field cross B at the origin. So for this, for experiencing a torque, you don't need the magnetic field for a magnetic moment for a magnetic dipole moment to experience a torque. You would not need the magnetic field to be non-uniform. In fact, a constant magnetic field would also give you this torque. And I want you to derive this expression of the torque given that this magnetic field is slowly varying, or maybe even if it is constant, then from this expression for torque, this density expression for the torque, I want you to derive this expression, where torque is given by m cross B. This, I think, you are familiar with this result, but I want you to derive this result starting from this density, torque density, and integrating this torque density over a given volume for an arbitrary j. You know what m is in terms of the j, right? So you know what m is, x cross j. This is m, and with this, or half of x cross j, x cross j, this is m. And with this definition of m for an arbitrary j, can you show that the torque is m cross b? That is your exercise. Okay, very good. Also, I would give you an exercise to find the force between two magnetic dipoles, two electric dipoles, and then also for an electric dipole, what is the force in an electric field? This has a very similar form. It is the gradient of E dot P. Again, E is varying. If E is varying, then this dipole the electric dipole also experiences a force, and it is given in this form. Okay, and so therefore, even ideal electric dipoles, they would experience a force, and therefore you can go ahead and consider two electric dipoles. So this is the expression for the force, and therefore you can find the effective force between two electric dipoles. So this also I'll give as an exercise. Okay, so please consult your, try to do them as a homework exercise. You are free to consult any textbook if you like, but at the end of the week we'll give you a problem, like a solution to the problem set, and then you can look at the solution set and basically convince yourself that what you worked out is right. Okay, so let me finish my discussion of magnetostatics here. There's one more discussion about energy in magnetostatic magnetic fields. So if there are static magnetic fields, what is the energy in the configuration? We saw that in electrostatics also we did a similar calculation, and we saw the electrostatic energy is given by the integral of E squared. So there is a question, what happens in magnetostatics? But unfortunately, in order to discuss that, I have to consider dynamics. Okay, so the reason for that is, in order to set a current up, let's say a steady current, we have to make the charges flow, and that is like a dynamical situation where we have to make the charges flow and set up a steady current, and that process, the amount of work done in setting up a steady current would be stored in the magnetic field of the steady current as magnetostatic energy. And that, in order to see that expression, we have to go through a process where the current is changing and dependent on time, and therefore, in order to deal with that scenario properly, let us discuss Faraday's law in all its glory, like with proper time dependence, in the next video, and then we can discuss the energy in magnetostatic magnetic fields. Okay, that one topic